tough act to follow. I think both acts. But literally, I jump out of the bed in the morning with a big smile on my face. And I do that for two reasons. One, I have a spectacular family. I have an inspirational wife. I have 5 daughters, so I'm looking for sympathy. Between the ages of, now get this, 6 and 11. Yeah. Work with me here, work with me. But the other reason I do it is I go to work at Bluebird and I live a dream. I get to work on a therapy that has the potential to cure, or at least dramatically transform, the life of a child that's been handed a genetic death sentence. So that, to me, is inspirational. And I'm going to tell you a story. I'm going to tell you a story in 3 parts. First, one of great sadness, and I hope it makes everyone extremely uncomfortable in the room. Then I'm going to tell one of great hope that comes back to gene therapy and what we're trying to do. And I actually had this line planned, which was, I call it super cool Buck Rogers kind of medicine. And I was going to pull it because someone else had mentioned Buck Rogers, and I thought that was actually a little strange. But you'll hear an amazing piece of science and medicine. And then third, and the reason I think I'm up here is there's actually a challenge, a concern, a big dilemma that sits out in front of us that I alone certainly can't solve. I hopefully can just push the envelope. So first, I'm going to ask a question. All of those of you in the room who have kids between the ages of 0 and 10, please raise your hand. Okay. How many of you in the audience or in the car, or whoever's listening, have witnessed a child somewhere below 10 or 12 years old die from a disease? Okay. So everyone, I think, in here should really pay attention to the next few words, because I do think we have an opportunity to make a huge difference. So first, great sadness. There's a disease called adrenoleukodystrophy, ALD for short. It was captured in a movie called Lorenzo's Oil. So some of you may be familiar with it. But imagine this. Imagine a child between the ages of 4, 6, 7, somewhere in that range. Mom, and usually mom, notices that something's not quite right in school, on the playground, somewhere. And if she's smart, which they usually are, bring them to the doctor. And if you're really lucky, the doctor will figure out in the first go-around that the child has a problem. Get the right medical tests, and then is handed a diagnosis of ALD. What just happened in that instant was that child was handed a genetic death sentence. So what do you do in that instance? And what is ALD? Interestingly enough, it's one problem. It's one problem with a cell in your brain called the microglia cell. Forget the details of all the biology, but that cell has a problem that it can't clear something called the very long-chain fatty acids. Forget that also. Just remember that when that builds up in the brain, you start to have a real big problem. And what you see on the screen here in a minute, right there, is on the far left-hand side, you see the brain scan of a 7-year-old child. And all you have to know about this scan is white is bad. You can figure out the rest. White equals demyelinization of the brain. White equals a buildup of these very long-chain fatty acids. And if you notice the time course on this slide, that's 2 years. Child on the left is everyone's child, all of our children. Child on the right is a child who's vegetative. The only thing that child, and the only way that child stays alive, is when does mom and dad decide to let go? Horrifying situation. Now, I think most of you probably are captured now, but let me just needle this a little bit more, okay? Because I want to make this extremely personal, and so I'm going to make those of you who aren't already uncomfortable a little more uncomfortable. I want you to meet Ethan. Ethan is now was the son of a friend of mine, who's a fellow CEO in the industry. Ethan, about 1.5 years too late, got to the doctor's office and discovered he had ALD. He's a 9-year-old boy in this picture with braces, thinking about the future, thinking about whatever a 9-year-old should think about. But in that instant, when they went to the doctor, and in this case, 1 year too late, they found out he had ALD. In this picture, which was less than 6 months from left to right, he's lying in his bed, and this was the last picture ever taken of Ethan. He died 3 months after this picture at the ripe age of 10. So if you're not uncomfortable, you're not human. And you should look at somebody. I take this picture everywhere. It's in my office, my cube. It's in my car. It's at home. I present this to my kids. And I walk them through it because this is the stark reminder why we must address the challenge that I'm going to get to you here. But let me shift gears on you a little bit just to make sure you're not totally depressed walking out of here. So let's talk about some great hope. Let's talk about gene therapy, but it starts with a game of Legos. I'm Danish, I like Legos. So let's start with a big Lego piece first, which was the discovery of something called the hematopoietic stem cell. Forget that fancy word, call it a blood stem cell. And if you don't like that, call it the Mighty Mouse of all cells. Okay? This is an awesome cell. My kids actually call it the mother cell. The reason they do that is you see, this cell turns into all kinds of things and wears all kinds of hats and does a spectacular job at it. It produces your immune system. It produces the cells in your blood system. It produces the cells in your CNS, in your nervous system, including the microglial cell. Bing, hopefully, all of y'all made the connection. I'm not from the South, I'm not sure where that came from. But you made the connection, the blood stem cell turns into the microglial cell. And that's the magic. That's where we figured out that at that point in time, you have two choices. You can either replace the blood stem cells in your body, or you can fix them. Next piece in the Lego game was, let's try to replace them. And they did. They took the cells out of the body of the child, they put the new ones in from someone else. And lo and behold, some of the cases, it actually worked. The process worked. There were some cells that got in the brain, but here's the catch. In a big percentage of the time, that treatment alone kills you. In another big percentage of the time, you don't even have access to that type of treatment. So I'm going to shift gears and go to the Buck Rogers part here and talk about gene therapy, saying, how do we fix it? How do we take that blood stem cell and fix what's broken? How do we take a gene from the outside and put it in that cell? It sounds remarkably complicated. It's actually extremely complicated. I don't understand half of it. But I'll walk you through it here, and bear with me here. There's a 3-minute and 51-second video I'm going to show you, because TED folks are pretty specific about their timings. So I'm going to take you through this video, and I'm going to talk you through it, because I think what you have to figure out is we have to make something that can penetrate a cell and insert a piece of DNA. So first, we got to make it. What you see here is the cellular manufacturing plant called 293T cells, for those of you who care. What they do, and they're really good at, is making things. Those little things you see slipping around, those are 4 plasmids. Those are 4 parts to the virus we're trying to make. You put them in there in parts, and the cell understands what to do inside the nucleus. It reads them, as you can see here. It produces 4 pieces of RNA. 3 of them bug out of the nucleus, go out there and produce the 3 components we need: capsid, a Reb protein, and the VSVG envelope. Again, forget all those fancy words, but those are the parts. Then, here's the key piece. That therapeutic piece of RNA, that's what encodes for that broken gene that's in the blood stem cell in the case of ALD. Here you see it packaged, and boom, right there. That's your virus. That's our Trojan horse. That's the thing. It's actually an HIV-derived virus that now has been hacked up and is produced, and now millions of those are sitting in this vial. Cool, but not that helpful unless you have the other half, which is you need the blood stem cell from the patient, from Ethan. And here what you're visualizing is you're going into the you're going into the marrow to pick out the blood stem cells. And you see these little red guys popping into the bloodstream? Those are the ones we capture. It's a fairly standard procedure. We stick billions of those, or as many as we can, into a bag. Now, next step, virus meets blood stem cell in the bag outside the body. So virus never goes in the body. What it then knows to do is to infect the cells. Infect it as many times as we can, as many cells as we can in that bag. It goes into first the cytoplasm, then it releases the payload. It then knows to, and we're certainly taking some scientific liberties here to make it a little more simple, but it explodes there, right there. That's your money ship, the RNA. But for those of you who remember your biology class, we got to do some gymnastics to make sure that turns into DNA. Because we have here, up here it says revolutionary ideas. Well, watch carefully here, because as we finish this gymnastics, you're going to visualize the revolutionary idea. This gets moved and transported into the blood stem cells compartment, the nucleus, where the DNA exists. And right here, in a little magic, boom, it integrates itself into the DNA. Now, what you've just created is a gene-modified blood stem cell. That stem cell knows what to do. The cells know what to do. It starts producing your therapeutic gene. It starts producing a lot of them. You turn your red cell into blue cell in this picture here. Bottom line, those are modified. Those now know how to do what the problem was before. We put it back into the patient. So picture Ethan here. We put it back in. Now these cells seed your marrow, and they then start to produce daughter cells. All those daughter cells now know what to do. They have a functioning copy of this gene. That's great. How does it compare to ALD? ALD, as you remember, in the brain had this buildup of white matter, or demyelinization, these very long-chain fatty acids. So what happens now is some % of these blood stem cells, as they continue to produce, turn into macrophages. That's this pretty cell. Once that cell moves, some % of those cross the blood-brain barrier. This is all pretty seismic in science, if you ask me, and it moves into the brain. It then sits there and acts like a sponge on these very long-chain fatty acids. And what happens is stabilizes the disease in not all the cases, but we certainly hope in many of the cases, depending on where the disease is. And you say, Nick, great video, wonderful. Who cares? It's a video. What you should care about is an awesome pair over in France, Patrico Borg and Natalie Cartier, did exactly what I just described. What you see on the left-hand side is an untreated patient. We went through that. What you see on the right is 2 patients that were treated over 5+ years ago. You don't have to look at a lot of scans or be a radiologist to realize that those 2 kids are doing pretty well. They're in the playground, they're at home, they're in school. Pretty amazing. What's also really cool, now let's zoom out a little bit and say, how does this apply somewhere else? Well, let me tell you about another disease very quickly. It's called thalassemia. This is a case where you can't make hemoglobin. If you don't get hemoglobin from someone else, you die, average age of 7. If you do get it from someone else, you can survive to the age of 30, 40 years old, perhaps, with a very tough quality of life. So what we do there is, instead of inserting the transporter gene, we insert the hemoglobin gene. So this funky slide that you have up here is the blood level in this patient who at the age of 4 has been dependent on someone else's blood since the age of 4 and was 18 years old. We treated him 1 time. At that point in time, red is good in this picture. We're now producing over 1/3 of his hemoglobin, and we're out 4+ years now with this patient, completely transformed life. It's never happened before in this disease. There's no way this is a spontaneous treatment because we can track every single blood molecule that's made with our virus, has a barcode on it. We can see it. And that was the genius of Philippe Labouche, our scientific founder, to figure that out, because that's how we know we're making a difference. That's how we know how to treat this patient differently. So that's great, Nick. This all sounds good. So what in the world is the problem, right? What's the challenge? Well, I think the challenge at this moment is that, are we ready? Is the system, is society, is the status quo ready to receive a treatment like this? It's pretty transformational, but here's how it kind of blows up the system a little. Let's take 3 viewpoints. First, the regulators. You talk to the regulators, what's the right balance? What are the right number of patients that they should require for this? How do they handle this kind of treatment? What are the hurdles put in place? Those are absolutely essential to folks like me. That's one piece of the equation. And I can tell you, obviously, my opinion is that balance is not quite right. That balance is skewed. It's a one-size-fits-all. Second stakeholder, even more confusing, the payer. They're great at saying, deliver a drug, pay for the drug. Here, we delivered the drug 1 time. The body is now the enzyme replacement system. And every time that body delivers drug, it doesn't pay very well, right? What do? What's the value of that type of treatment? Forget the price. What's the value of that treatment? I described to you Ethan. He had a battle for 8 months. That battle cost over $3.5 million. That's a big number. So how do you think about it from a payer point of view? And then thirdly, from my point of view, an industry point of view, bigger companies, smaller companies, how do you put all this together? How do you think about if the regulators put up a lot of hurdles and the payers don't understand the value, how do you justify spending hundreds of millions of dollars to take the science and medicine like this forward? The answer is it's complicated. The answer is we got to do a much better job putting in context how we balance the science and medicine that we're bringing forward with the stakeholders. We need to rise above and figure out a way to realize that that gap that could potentially exist between the time that we're ready to deliver this to the market and all these other therapies we're bringing forward, these stakeholders better be ready. Because if there's a gap, patients die. Ethan dies. And that's not acceptable to me. I live under the edict that every child should have the opportunity to have an ideal day. And what we say at the place I work is every child should have the right to have a bluebird day. Thank you.